Alright, now that we know that light can behave both like particles and waves, let's actually look at some properties of light. And first, we're going to talk about atomic spectra. That is, atoms or molecules. They're made up of electrons, and electrons make up light as well. They can absorb and release energy, and they do this as light. And you'll know this by looking at fireworks and neon lights. That's what's happening there. And if the light that is emitted from an atom or molecule, if you separate that through a prism, you can see that each type of element has a unique pattern of light that it will give off. We call this an emission spectrum. And it's non-continuous, that is, the wavelengths of light are very discrete. And we can use this if we have an unknown material. If we just heat it up, we can see what kind of light comes out and determine what that material is. So here's the basic experiment where we have hydrogen and we shoot it with electricity, and the light that comes out, we pass it through a slit so we make sure only the light from hydrogen is going into our prism. And this prism will split the light into its different colors, and if we have some kind of film, we can see what colors are being emitted, and we see that there's only 4 colors here being emitted. And so let's look at 2 different spectrums. Helium, here we actually have 6 colors being emitted. If we look at barium, we have multiple colors, but they're all discrete and they're very unique. And here's the whole white light spectrum, all light going from red to violet. Now, identifying elements through this process is what's called a flame test. So if you have an unknown metal like sodium, potassium, lithium, and barium, if you put them in a flame, you will get very different colors of light out. And this is because the electrons are being excited by the energy and then letting out the lights. And if you look at emission and absorption, they're opposites of each other. So at the top here, we see we have many different bands for mercury, and for absorption of light, if you shine light at mercury and then measure the light that came out the other side, that is the light that wasn't absorbed, you'll see you'll have these dark bands. And what this is telling us is that the wavelength of light that is emitted by mercury is the same wavelength of light that is absorbed by mercury. And we actually have an equation to measure this stuff. And the person who made this, his name was Rydberg, and what he did is by using the hydrogen spectrum, his equation can predict what wavelengths of light should be emitted, and that equation is 1 divided by wavelength equals r, which is his constant, just a number, then 1 divided by m squared. A lot of times when you see this, they also call this variable n, but I have it here presented as m. That's just your initial energy level, minus 1 divided by n squared, which is your final energy level. So if you know your initial energy level, your final energy level, you can say what wavelength of light is being emitted. Now, Rydberg wasn't sure why we saw these emissions at these specific wavelengths. He just knew that we did, and he could predict them. So let's try this out. So I have light that is being emitted from a hydrogen atom, and I want to know what spectrum this light will be found in. So I'm going from energy level of 2 to energy level of 1. So what you want to do is, using the equation on the previous page, calculate out the wavelength. Then with that wavelength, look at the electromagnetic spectrum and tell me what type of light that is. So pause the video, try that, come back when you have an answer. Alright, so let's take a look at it. Here's the Rydberg equation. I have it in the m form for initial. So I plug that in, 1 divided by wavelength equals his constant, 1 divided by 2 squared minus 1 divided by 1 squared. Then I have 1 over wavelength equals 8.235 times 10 to the 6, But I want wavelength, not 1 over wavelength, so I just need to flip this whole equation. And I get wavelength equals 1.214 times 10 to the minus 7 meters. Now our electromagnetic spectrum isn't in meters, it's usually in nanometers, so let's do that conversion right now, where 1 times 10 to the minus 9 meters is 1 nanometer, and we get that the wavelength of light given off is 121.4 nanometers, or UV light. Alright, so that's it for this video. In the next one, we'll start looking at why atoms give off light. See you then.